Hello everyone. In this video, we will discuss about the answer for the question number 48 that was asked in GATE 2023. So the question is asking to find out the speed of the motor when the supply voltage is reduced by 20%. Supply voltage and frequency are reduced by 20%. And given conditions are the machine is operating at constant torque load and at rated speed and delivering rated output. So before directly going to the answer, we will discuss about how the torque equation of a three-phase induction motor can be derived. So consider this circuit which represent the rotor circuit of the induction motor. So we are having the EMF induced in the rotor, the resistance of the rotor, and the reactance of the rotor, and the frequency of the rotor. So EMF induced per phase in the rotor winding is equal to E2 of S is equal to S into E2 of 0, where S is the slip of the machine, and E2 of 0 is the induced EMF in the rotor at standstill position. That means E2 of 0 is the EMF induced in the rotor when the rotor is not rotating. When rotor is not rotating, the EMF induced in the rotor will be the maximum, and if it is rotating, then the EMF induced in the rotor will start to reduce. So that is what is that is what we can refer from this equation. And the resistance, coming to the resistance of the rotor circuit is fixed. It is independent of the slip. And for reactance, we know reactance is equal to 2 pi f to omega into L, where omega is the angular frequency of the current flowing through this circuit. So the frequency of the induced current in the rotor circuit is equal to slip multiplied by the stator voltage frequency. So here the frequency of the current induced is S into F1. So we will substitute that here, and that will lead to the reactance of the rotor circuit as S into X2 of 0, where X2 of 0 is the reactance of the rotor and at standstill position. So now we have evaluated the four parameters of the rotor circuit, that is EMF induced in the rotor circuit, frequency of the current or voltage in the rotor circuit, as well as reactance and resistance. So from we can see reactance and frequency and EMF induced are depending on the slip, whereas the resistance is independent of the slip. So this we have to keep in our mind. Now we will go to how the equation for the power developed, active power developed in the rotor circuit. That is given as 3 into E2 of S into I2 of S into cos phi 2 of S, where E2 of S is the EMF induced in the rotor circuit, I2 of S is the current flowing through the rotor circuit, whereas cos phi 2 of S is the power factor associated with the rotor circuit. And this 3 represents 3 phase. So this equation represents the 3 phase power developed in the rotor circuit. Now considering I2 of S, I2 of S is the voltage by voltage in the rotor circuit divided by impedance of the rotor circuit, where voltage is the EMF voltage induced, that is E2 of S, divided by the total impedance of the circuit, that is Z2 of S, and the power factor is resistance by total impedance, that is R2 by Z2 of S. So now from this formulas, we can substitute those formulas here, and we will from here we can see E2 of S is equal to S into E2 of 0. We will substitute that here, S into E2 of 0, S into E2 of 0 here, and R2 is same as R2, and Z2 of S is R square plus the reactance square, that is R square plus S into X2 of 0 the whole square. So these identities we will substitute here, and that will eventually lead us to this equation, that is the 3 phase power developed in the synchronous 3 phase induction motor is 3 into S square into E2 of 0 square into R2 divided by R square plus Sx to the whole square. This is similar to 3 into I square into 2s into R2, because if you are taking this 3 R2 outside here, the remaining term is s square into e square 20 divided by r square plus sx20 the whole square. So taking the square term outside, we can have this equation in this form. So we know s e20 is the EMF induced, and r square plus sx20 the whole square is the total impedance of the circuit. So EMF induced divided by the total impedance of the circuit, that is equal to the current flowing through the circuit. So now this is equal to, this whole term is equal to I2 of s. So this equation will transform to this, and this represents the copper loss in the rotor circuit. So what we can conclude is all this power is dissipated at I square R, that means copper loss in the rotor circuit. Now let us find the equation for copper loss. Suppose let TD with the developed torque in the motor, Ns is the synchronous speed, Nr is the rotor speed. So the power transferred from stator to the rotor, that is the air gap power, or air gap power equal to the angular velocity of the means omega s into Td equal to 2 pi ns into Td, and total mechanical power developed by the rotor equal to omega r into Td, that is 2 pi nr into Td. So this is the air gap power, and this is the mechanical power developed by the rotor. So the losses correspond to the copper losses. So the losses is equal to the input power minus the output power. So with that equation, we will have copper losses equal to 2 pi ns Td minus 2 pi nr Td. 2 pi ns Td minus 2 pi nr Td. So copper loss is equal to 2 pi Td into ns minus nr. This is the total I square R loss in the rotor circuit. So dividing that with the input power to the rotor, that means air gap power, which is 2 pi ns into Td, we can have the ratio between total I square R loss in the rotor and the air gap power, or the input power to the rotor, is ns minus nr by ns, which is nothing but the slip of the machine. From there, we can have the total I square R loss equal to S into input power to the rotor. Again, this we have developed here, 3s square E20 square into R2 divided by R square plus Sx20 the whole square. So that we will substitute here. That is equal to S into input power to the rotor, that is omega s into Td, that is 2 pi ns Td. So the total copper losses is equal to S into 2 pi ns into Td. After simplification from this equation, we can have the torque developed in the rotor equal to 3s E20 square R2 divided by omega s R square plus Sx20 the whole square. This is torque developed in as three-phase induction motor, and this equation is very important when it comes to competitive exams. So now going back to the question, we can see the load at it is the motor is operated at rated speed, and that means the slip of the rotor is very low, because when the motor is operating at rated speed or close to the rated speed, the slip will be very low. This S value will be very low, and in that case S square will be even lower. So at rated speed or close to rated speed, very close to rated speed, we can have S is very small, hence this R square will be far greater than Sx20 the whole square. So with this approximation, we can neglect this Sx20 the whole square, and this equation can be transformed to this equation where Sx20 the whole square is neglected, because this will be very small compared to the R square value. So we can have the approximation as TD directly proportional to TD approximately equal to 3 into slip into E2 of 0 the whole square divided by omega s into R. Now we can have further approximations here, and that is, if you are neglecting the stator impedances, this E2 of 0 will be equal to or can be approximated as the supply voltage. So in that case, we can substitute E2 of 0 as V, and this equation will transform to this equation, and TD approximately equal to 3s V square divided by omega s R. This equation is got by assuming that the stator impedance is negligible. So finally, we can have TD directly proportional to S V square divided by R. Sorry, S V square divided by omega s, because 3 and R are constant. So TD, the torque developed in a induction motor, 3-phase induction motor, is directly proportional to S V square by omega s, which is directly equal to S V square by F, where F is the supply frequency and V is the supply voltage. Actually, this equation is very important, and many questions have asked from the other competitive exams as well as from GATE exams. So keeping this equation in mind is very important. Now coming to the solution, we have the synchronous speed equal to ns equal to 120 f by p. For the first case, the f value is frequency is 50 hertz, so 120 f by p equal to 1000 rpm, and slip is 0.04. And from here we have TD directly proportional to SV square by F, and in question it is mentioned that torque is constant. That means TD1 equal to TD2. So S1 V1 square by F1 equal to S2 V2 square by F2. So S1 we have find out from here, that is 0.04 into V1 square. So V1 square divided by F1 equal to S2, that is what we have to find, into 0.8 V1, because in the second case the voltage is reduced by 20%. So the new voltage is 80% of the previous one. So the V2 equal to 0.8 into V1. You will substitute here. Similar in case of frequency, because in the second case the frequency is 80% of the previous frequency. So substituting this and solving, we will get S2 equal to 0.0105, which is the new slip. Now we will calculate the new frequency, because now the supply voltage and frequency is changed. So the new frequency is 0.8 into F, that is 40 Hertz, and the new synchronous speed is 120 into 40 by 60, that is 800 Hertz. So now we have the new slip and the new synchronous speed. From there we can have the new rotor speed, that is 1 minus new slip into new synchronous speed, which is 1 minus 0.05 into 800, which is equal to 760. So this is how we can reach at this answer. So the most important thing is this equation. So this relation is very important, and questions from this relation is asked in the previous years. So keeping this relation in mind is very important, and all these are derivation to this equation. So if you are aware of this equation, you can easily solve this problem. And these are the NPTEL reference lectures that you can refer to understand how this torque is derived, this torque equation is derived. So that's all about the answer. Thank you everyone.